In this chapter, we're going to explore how large language models, which are, absolute masters of text, can be taught to understand and even reason about the visual world. It's a really fascinating journey that bridges the gap between language and sight, and it dramatically expands what these AI models are capable of. We're going to get into the key architectural innovations that make all of this possible.
So, here's our roadmap. First, we'll talk about why going beyond text, this idea of multimodality, is so crucial in the first place. Then, we'll dive into the technical building blocks, starting with something called vision transformers that let models see. After that, we'll look at CLIP, a model that's all about creating a shared language for images and text. Then we'll cover Blip2, which is a super efficient way to get LLMs chatting about pictures. And finally, we'll see it all come together with some really cool examples.
Okay, so why do we need our AI models to do more than just read text? Well, think about it. In the real world, language almost never exists in a vacuum. It's grounded in our physical environment, right? It's enriched by visual context, by what we see around us. So if we want to build truly intelligent systems, we have to give them the ability to perceive and integrate information from all these different sources. By giving models eyes, so to speak, we unlock entirely new capabilities and let them tackle a whole new class of problems.
I mean, just pause and think about this question for a second. This is really the core idea driving this entire field. Imagine the possibilities. What if a language model could not only read a technical manual, but also look at a photo of a broken engine and walk you through how to fix it? That's the kind of power we're talking about when we add vision to language.
Now, before we get any deeper, let's just make sure we're all on the same page with a key term: modality. It sounds fancy, but it's really simple. A modality is just a type of data. Text is one modality. Images are another. Audio, video, those are others. So when you hear us talk about a multimodal model, all we mean is a single AI system that can process and understand information from more than one of these types. Simple as that.
So, the big question is, how do you actually get a model built for text to understand something visual, like an image? For a long time, computer vision used its own special tools, like convolutional neural networks. But the huge breakthrough came when researchers figured out how to adapt the transformer architecture, that's the T in GPT, to work with images. This elegant solution, the Vision Transformer, or ViT, really changed the game by basically treating vision as a kind of language problem.
The core idea behind the vision transformer is just a brilliant analogy. Think about how a normal language transformer works. It takes a sentence, it breaks it up into pieces called tokens, basically words or parts of words, and then it turns each token into a numerical vector called an embedding. The ViT just cleverly copies that exact process, but for images. It tokenizes an image not into words, but by slicing it into a bunch of smaller patches. Then it turns each of those patches into an embedding. It's the same fundamental concept, just applied to pixels instead of text.
Let's walk through this step by step. First, you take your image and you slice it up into a grid of little squares, kind of like cutting a photo into a set of tiles. Each of those little 2D patches then gets flattened out into one long single line of pixel values. Then, and this is the key part, a mathematical operation called a linear projection turns that raw string of pixels into a meaningful numerical embedding. Once you have a sequence of these patch embeddings, you can just feed them into a standard transformer. From the transformer's perspective, it doesn't even know the difference. It's just crunching a sequence of vectors, whether they came from words or from pictures.
This quote from the original ViT paper just captures the idea perfectly. In their first implementation, the visual words, or patches they used, were 16 by 16 pixels. So a big image would get broken down into a long sequence of these 16 by 16 pixel tokens, all ready for the transformer to read.
Okay, so the Vision Transformer gives us a way to represent an image as a sequence of tokens. That's great. But that brings up the next big question. How does the model learn that a certain pattern of visual tokens actually means dog? The next challenge is to connect the meaning of these visual things to the meaning of actual words. And that's exactly the problem that a model called CLIP was designed to solve.
The big idea behind CLIP is the creation of a shared multimodal embedding space. You can think of this as a huge, high-dimensional map where every concept can be plotted as a point. What CLIP does is it learns to put similar things close together on this map, no matter if they started as a picture or as text. So the magic is that the vector for a photo of a puppy will end up right next to the vector for the text, a photo of a puppy. They share the same neighborhood on the map.
And that, in a nutshell, is the goal of CLIP.
It's trained on a ginormous dataset of images and their captions from the internet. Its entire job is to learn how to produce embeddings, where the matching image-text pairs are mathematically close and all the non-matching pairs are pushed far, far apart.
The way CLIP is trained is actually pretty elegant. In each step, the model looks at a batch of, say, 100 images and their 100 captions. It encodes all of them into that shared space. Then, it calculates the similarity between every single image and every single text caption. The model then gets one simple instruction: increase the similarity score for the pairs that actually match and decrease the score for all the ones that don't.
This training technique is called contrastive learning, and it's a really powerful idea because it's kind of like how we learn. The model doesn't just learn to label things in isolation. It learns by contrasting positive and negative examples. It learns what something is by also learning all the things that it is not, and this forces it to build a really robust and nuanced understanding of concepts.
So what's the big deal? What can you actually do with this shared vocabulary? Well, it turns out a lot. You can do what's called zero-shot image classification, where you can classify images into categories the model has never been explicitly trained on. You can build powerful search engines where you type in text and get back images, or you put in an image and get back similar text. And maybe most famously, this is the core technology that guides generative models like Stable Diffusion, telling them how to create an image that actually matches a text prompt.
All right, so we have our building blocks. We have VIT to see images, and we have CLIP to connect that vision to the meaning of text. The next logical step is to put these together to create an AI that can actually have a conversation with you about a picture. And that brings us to a really clever architecture called BLIP2.
Now here's the problem. If you wanted to train a massive, generative, multimodal model from the ground up, well, good luck. It's incredibly expensive, it requires billions of image-text pairs, and just an astronomical amount of computing power. It's just not practical for most people.
BLIP2's solution to this problem is both clever and incredibly efficient. Instead of starting from scratch, it says, hey, let's take these powerful pre-trained models that already exist, an image encoder and a large language model, and let's freeze them. That means we don't change them at all. The only new piece we're going to train is a tiny little bridge model that learns how to translate between the two.
So let's look under the hood. BLIP2 has three main parts. First, you have a frozen image encoder, like a VIT, which does the scene. Second, you have a frozen LLM, like Llama, which does all the heavy lifting for reasoning and text generation. And then, connecting them, you have the star of the show, the Q-former. This small, querying transformer is the only part that gets trained. Its whole job is to learn how to ask the right questions of the image encoder and package up the visual information in a way the LLM can digest.
The training for this is a really smart two-step process. In stage 1, the Q-former learns what to see. It's trained to interact with the frozen image encoder and pull out the most important bits of visual information that are relevant to a text caption. Then, in stage 2, it learns how to talk about it. The output from that trained Q-former is then fed into the frozen LLM. This output acts like a soft visual prompt. It's not text, but it's a set of instructions that guides the LLM's text generation, telling it what's in the image.
Okay, that's a lot of theory. So let's make this more concrete and look at what these models can actually do. We'll check out a couple of examples to really see this technology in practice. The most basic application is just simple image captioning. You give the model a picture, and it spits out a sentence describing it. And as you can see here, you give it a photo of a supercar, and it generates a perfectly accurate and descriptive caption. This is the foundation for a lot of other tasks.
But where things get really amazing is in conversation. Look at this. After the model identifies the car, the user can ask a follow-up question, like, what would it cost me to drive that car? And the model can give a reasonable answer. This is so important because it shows a true fusion of abilities. The vision part sees the car, and that information is passed to the LLM, which then taps into its huge store of general knowledge about the world to reason about the price of supercars. It's seeing and thinking combined.
So, to quickly recap the main points, vision transformers are the trick we use to turn pictures into tokens that language models can read. Models like CLIP then create a shared map where the meaning of those visual tokens and text tokens are aligned. Then, clever architectures like BLIP2 use these pieces efficiently to give powerful existing LLMs the gift of sight. And all of this together is what enables this new wave of AI that can see, understand, and talk about our visual world.
This really brings us to our final thought. We've spent this whole time talking about bridging vision and text, but that's just the beginning of true multimodality. The principles we've discussed can be extended to other senses. So the real question to leave you with is this: what new, incredible capabilities are we going to unlock when AI models can perceive and reason about the world, not just by seeing, but also by hearing, touching, and eventually acting within it, just like we do?